So the topic for today is sort of legal issues, and I posted some of the papers on Fronter. There is one paper also which we didn't discuss last week, is about the rigor. So maybe we start with the first two, which discuss the sort of privacy and legal considerations. Let's open my page. Oh, which papers have you guys read? The two marked?
Yeah. Well, I tried.
You tried?
I mean, it was very the different end of the scale. Both of them. One is very technical
and the other almost not.
The other one's very.
That's right.
Easy to read, so.
That's right. So they are two representative of completely two different styles.
And the interesting thing is that the easy reading paper tells you that it's up to the vendor or the developers to protect you in some way. And they take care of it, and the other ones say they do not take care of it. It's open, it's just a lot of leaking.
Exactly. So yeah, before we start, what do you think? Whose responsibility is to do that? Is it the developers, or is it the kind of legal and social systems?
The developer has to follow the legal systems, of course, but there is no legal system. Of course, the developer couldn't care less about it. Or maybe actually they care about it the other way, because they can sell their rights in some way to others. So it's So that's probably why you need a legal to protect you as a user or us as a user.
Yeah, exactly. So with that one, it is quite, yeah. So these guys were trying to say it's not our responsibility, it's the developers, because they have the direct control of what happens. But it's actually the other way around. It's the indirect control of the law, which kind of forces the developers to do certain things certain way, not leaving it up to the developers. Yeah, obviously there are some issues. So the more technical one sort of identified some important aspects of how the privacy kind of works currently, that you're granting permissions, but you don't know what happens after that data is kind of captured. So,
and also, I don't know if it's right, but it seems like you can only accept the package you get.
Yeah.
You cannot switch out. Okay, I get two of them, it's fine, but the other two I don't want to have. So, but it seems like, okay, it's four, and you have to accept all of them.
Yeah, exactly. So yeah, let's we will discuss it a little bit in more detail after. Marcus, you want to present the papers?
Yeah, I can present.
Yeah, so let Marcus present the papers first, and then we will have a discussion of what we think. Yeah. Okay.
Okay. So it's in purple.
I obviously I forgot the cable again. So, but you have the.
Like always.
You prepared. Excellent.
Okay, so I've read the
first paper on the list. It's actually not a paper, but it's kind of a European Union Commission, and they are making some new frameworks for mobile applications. And first I started out finding out why they are making new ones. And the current rules are made in 1995. And in 1995 we didn't have much of social media or the large collection of data that we have today.
Yeah.
And in 2011 they found out that only 26% of social network users and 18% of online shoppers thought that they had complete control over their personal data. And 43% of internet user was asked for more information than actually necessary to use the services that asked for the information. And they are also making these European guidelines because there are a lot of national guidelines that you have to follow to have your application distributed in the European Union. And I have a picture. And people are not always trusting the services that they are providing their personal information to. So what the Commission is doing is to update the old principles, the Data Protection Directive. And the probably most important point I found was that everyone should have a right to be forgotten. So if you enter some personal information, you should have the possibility to remove it again. And whenever a service is going to process your personal information, you have to give consent. Now they actually just can assume that you have given your consent because you are using the service, but now you explicitly have to do it. There is also a new need now that you have to notify whenever there is a serious data breach. So what do you guys think is appropriate delay from a breach to a notification if it's like credit card information and such? Anyone has a clue?
No time at all.
No time at all. So in 2011 there was a breach with many millions credit cards and such, and it took 1 week before the service actually said that okay, the information is out. So they are now saying that it should take no more than 24 hours. It doesn't take 24 hours to empty a bank account, I think. So it's probably too slow, but that's what they are trying to upgrade it to. And the good thing about the new rules they are trying to make is that it should apply to all companies that are serving citizens of the European Union. So even American companies has to follow the rules actually, because they are letting European citizens use it. Yeah, and that was it actually. They didn't have a lot of information on their webpage. Any questions?
Yeah. Maybe. I'm just interested in the ruling from the because this new one, they tried to make a new one in 2012 or something like that, but it didn't succeed. What was the reason? You know that?
No.
Why did they fail?
No.
Did you see anything, Marcus, about that?
No.
Why they failed of getting the new one approved? I guess that was the same. It made a lot of noise in Norway. There's a lot of discussion about this EU data protection if we had to adhere to that one. But I never got into the details. So I don't know.
Yeah. Yeah, the situation in Norway is quite interesting because of the quite transparent data laws here, that some information is actually public, whereas in some countries it isn't.
Yeah. Like the income.
Like the income, for example. So there is this balance between transparency and privacy. So obviously some things are clearly private, but some things I think Norway does well because it kind of enhances the transparency of public services and so on. And it's sort of better if you sort of trade off some of the privacy for transparency. But yeah, I don't know why in 2012 it didn't go through. The law for the right to be forgotten is quite controversial. It's kind of against what internet is in a sense, because you do have the internet archives and everything which kind of was public is public. So like if an article published an article about you, like let's say you've done some crime and the Aftenposten published an article, then this article is in this newspaper forever. It's not like you can go back and delete it from that newspaper. It's just that getting to that newspaper is not that easy because you have to go to libraries, you have to find the archives, and you have to dig that article out. So, you have to make certain effort to get to old articles, but they are still there. On the internet, it's the same. You can get to old articles, which are there, but it's very simple. Everybody can do it in 10 seconds. So some things which are published about you and stay there, they are kind of like the same as it was before. It's just the easiness of getting it out is much simpler. But the law says that you can actually delete some of the things which the search engines index and so on. They can be sort of unindexed. So you can't require the articles to be deleted, but you can require the links to the articles to be sort of wiped out, right? So it's harder to find it. It's as hard to find it as with the old media font, maybe. So that was the kind of the rationale for it. But I don't know, like what do you think? If something is online and the search engines indexed it, what do you think? Would any of you want to delete something about you which you find online from search engines? Maybe.
Would anyone? What's the question again?
Would you ask Google to delete something which Google indexed about you?
That would be a tough thing to do.
Because it is, I don't know, I mean, to me, it looks a little bit as if you could manipulate the reality in a sense, right? So you could just check everything which is about you and ask Google to only delete the things which kind of show you in slight negative way, maybe, and leave everything else on, right? So you kind of can use it to engineer the reality of what actually is there, if only some things are kind of visible and some things are not visible. But I mean, we're not celebrities and we're not having a lot of stuff written about us, so we kind of have a different perspective on it. But then from the other hand, the public figures, they kind of are public. So yeah, I don't know. What do you think? What do you think about this right to be forgotten? The Americans were making a lot of jokes about it. Yeah.
Sensitive information about someone online. I think it should be possible to at least hide it somewhat.
Yeah.
They're not just out there for all to see easily.
Mm-hmm. Yeah. I mean, as a side effect, Google offers a service now, so you can go and say, well, those pages talk about me and I would like them not to be indexed. And they will remove it from the index if you have a valid claim and the page is actually about you, right? And it doesn't matter whether they are negative or positive. Yeah. Yeah. So it is kind of interesting to observe what will happen and what will happen with the European Commission directive and how they will sort of shape it. But it is an important issue, the legal framework. It's not something that can be left to the developers. It's something that the society as such has to regulate. And then in the directive, they also talk about other countries, right? So it's not only for European Union countries, it's also for services which serve European Union citizens, but also about the data which leaves the European Union and sort of is transmitted overseas. There are some provisions of how this should happen and what are the implications of this happening, and how the data should be protected elsewhere. Yeah, reporting the bridge of data. Yeah, that's kind of yeah, it's a complicated issue, right? So if you're a service provider and you had a bridge and some of the things leaked, sure, you should notify, but you also have to prevent the bridge to propagate. So you have to find out why there was a bridge and also how to stop the information to leak. And sometimes it takes them longer than a day to find out, right? So in the other case, it could have, taken them a week to find out why, what was wrong and what was not secure and why the hackers or whoever got in. So you can't make a public announcement about the bridge if you don't have things under control. Yeah. So yeah, that one was sort of not a research paper. It was more of a kind of a specification of the legal framework of how, yeah, what sort of legal system can be put in place to help protect and control the flow of data. The other two articles, yeah, the 4 billion little brothers, not very technical, quite an easy to follow one. So who read that one? Yeah. So what do you think? So most of the things they talk about are kind of common sense. I mean, that was 2009, so some of the things might be kind of novel, but they did point out the GPS and the location and the accelerometer, the activity, and so on, the kind of the tracking aspects, the live logging aspects. We talked about it in the context of quantified self. And the kind of privacy aspects. One thing they've missed was that they sort of looked at individuals being tracked by their own devices, which is not as hot or controversial nowadays because we got used to this idea. But the idea of the phones tracking others is sort of something which they haven't mentioned, right? So if I'm wearing Google Glass, it's not just me being tracked, it's everybody else being tracked by me. So there is kind of a technology which is even more invasive in a sense of privacy, that it's not something you may have a full control over. So it might be, as we were discussing, I might be wearing a recorder which records a video and audio of everybody in this room, and that's sort of, I'm doing it, and you have no knowledge or control over that. Because we're getting to a point where those sort of capabilities are being possible. The other one was, it was a little bit waffly in a sense of pushing the responsibility to the developers. And it's quite naive to think that, right? It's quite naive to say, well, the developers will do the right thing. They don't. They do the right thing for the business which they are in, but not necessarily for the customers that the application is kind of targeting. So yeah, it is a little bit dated. In 2009, that could have been a good summary of what the capabilities are, but these days it's something a little bit dated, and also the challenges that they kind of identified are kind of something which we all know. They didn't propose anything new. One interesting one is this sort of the data granularity. What are the chunks of information that we want to protect? And that is part of the European Union directive and part of the other article as well. The other article kind of goes a little bit more into details of why the current security models are not ideal. All right, so who read the technical one, the Paint Droid paper?
Parts of it.
Was that? You started?
Yes, parts of it.
Yeah.
Yes, read the first maybe 10 pages, and then I jumped to the table to see the result more or less, because I was interested in the result.
Yeah.
But it was very technical.
Yes, it's a very technical paper. So who understood all the technical things they talked about? How the actual tracking happens? It will be on the exam.
At least I learned something about how Android is built, so it was, for that sake, it was good.
Yeah, all right. So I'm joking, obviously. I will not ask you about Dalvik and how the dispatch of methods works and so on. But there are some important things here. So one important thing is how the permission system works. So can someone summarize how the Android permission system is kind of organized? So one thing you mentioned already, that it's kind of packaged. So you have a certain number of permissions that you're granting the application to use, but you either grant all of them or none. If you grant none, you can't install the app, basically, and if you want to install the app, you have to grant all, right? So if the app asks you for the location service and for the identity of the SIM card and your contact list, you kind of give either everything or you don't install the app. Once you grant the permissions, they are granted, and you have no control when and how the application uses them, right? So there are some apps which you can use, and they kind of mock the permissions, right? So it sort of works like this. You have a new app, and the app asks for location, internet access, and identity. Okay, so and you want this app to be installed, but you don't want to give all those things to that app. So this is your phone. This is a new app which you want to install. What you can do is you can install, and this is your hardware. So this is where all the services live here. So you can install an app which hides your real services and pretends that this app will have access to all three, but actually it will have access to all three which are mocked by this layer instead of the real one, right? So I can say, okay, you will have the location and internet and identity, and this layer gives access to those three things. Every time, and now I install this app, every time this app asks for a location or something, I can have a notification, or I can have a policy of what to do, right? So if it asks for GPS, I can say, okay, I just want every time this app to get a fake one of London or whatever, right? So I have hard-coded some location, which the location service reports to this app, and this app has that fake one. If the app wants to have access to the internet, I can see what the app wants. Is the app sending something or reading something? And then I can either grant or not grant permission to that. And the same for identity. I can have a fake sort of a username or Gmail account or whatever, and then every time the app asks for this, it kind of gets the fake one, right? So I can kind of hide myself or protect myself under this kind of a thin layer of indirection of actually hiding the real services from the ones which are reported to this app. You can only have that if you have the phone rooted, because to do that you have to sort of pretend to be a system service that actually lives in the user space, right? So this app is in user space normally, but if you have root access, you can grant some of the things to have super user level access, and also you can mock some of the API to have kind of to pretend to be a system level service, right? But you have to grant this app this sort of the abilities, and you can only do that if you rooted your phone and you have the root access. Without it, you can't do that, right? So without it, you cannot have this layer, and you cannot have this sort of a detailed control of what happens. So there is kind of a flaw, right? So the current Android and iOS permission system is slightly flawed. What's the difference between the iOS and Android permission system?
Can't you in Android? So now in iOS, go into the settings and say that the one app don't get the location.
That's right. So in iOS, you have a little bit more fine granularity, because you can, when the app installs itself, it doesn't ask you for a lot of permissions. It sort of installs itself, and then you grant the app the permissions to certain things the app wants. So the app will ask you, oh, can I use the location? And you can say yes or no. And then if you said yes, later on you can go to settings and say no. And then it asks you, oh, can I push notify you about something? And again, you can say yes or no, and then you can go to settings and change it afterwards. So you have ability to turn on and off some of the permissions per app, per permission. With Android, you currently can't do that. They are planning to have something like that, but it's not there yet. So you either accept the package or you don't accept the package. So unfortunately, that's quite coarse-grained, and it's not flexible enough, right? So iOS in that respect is slightly more privacy conscious and a little bit more flexible, because you can have apps to which you didn't grant the permissions. So what will happen to the app which requires you to have a permission and you haven't granted it? Have you had situations like that?
With iOS,
Yeah.
it will work, but then the stuff that needs the camera, for instance,
don't work. Yeah. So some functionality which requires that particular feature will just not work. So I just recently got an app which asked me to grant the permission to the camera. I said no, and then the app kind of loads the front screen and doesn't do anything else because you're supposed to scan the code with the camera, and I said no to the camera, so it sort of got stuck in the initial stage. For the developers, it's quite tricky, right? So from Android point of view, if you're Android engineer, you guaranteed that if the app has installed, you have all the things which the app's supposed to have. You can have the required and optional features, and then the required ones are sort of present. So your coding and your logic is sort of a little bit simpler. With the model of iOS, where you can or cannot have it, you have to plan, situations where you have it or when you don't have it. what you do. So your kind of coding and so on has to be a little bit more complex, because you have to allow that the app will be installed on systems without certain functionalities.
Just have to check before you run it.
Yes. So it's the same on Android for the non-required features. Like, it's the same. If you have certain features, you can do some things, and if you don't, you can't. So it complicates the code base, but it's a little bit more flexible model of allowing users to run on limited capabilities devices or not granting certain permissions. There was an interesting change in iOS, the previous version, I think. So historically, you could get the ID of the SIM card and of the device from the API. You could ask what is the unique identifier of the device. And then they said, well, you can't do that anymore. So the normal approach was, you have, let's say you want to identify a users. So you want to check if certain user did something or achieved something in the on the particular device. So, you know, the user installed the so let's say I'm a developer, and I have 2 users, and they installed my app, and then I don't know, that user achieved something, like, let's say it's a game and they got to level 2, and this got to level 1, and then I need to know which one got to one or the other, and they don't need to log in. So how people are doing it, you get a unique ID of that device, of the SIM card or something, and then you send the level with that information, so I can uniquely identify out of the thousands of users using my app, which one is it, right? If I can't get this information, how you could do that? What's the simplest way to do the same without being able to read the unique ID of the SIM card?
Just assign a random user ID.
Exactly. You just generate, for example, you know your UID, uniquely global universal ID kind of thing. So you generate a random ID, and then you use that with the level or whatever, and that uniquely identifies the device, right, for you within your app. It's just that it's kind of uniquely identifying your app without uniquely identifying the user, because we don't know what SIM card that user is using or whatever, right? It's not a global ID which I can cross-check with other apps. It's something that only my app is using, and other app also has a unique one. So Apple did sort of a change, and a lot of people have to change their code because they were sort of using the cheap version of using the device ID. What's the advantage of doing that? What's the other advantage of doing that?
Anonymity.
Say it again?
Anonymity.
Anonymity, and also if the user decides to use a different device, you can kind of identify them even if they change over the device, right? Because it's not tied to the hardware platform. Yeah. Okay, so what these guys were doing was they try to check, once you read sensitive information like user ID or a location, how that information is being used. Correct? In this paper.
Or even the big one.
Yeah, in the big one.
What did you say?
Yeah. So what? Yeah. How the app was working? What was the main idea behind?
It was a layout process, and it was trying to make this less performance training as possible. And it was an improvement for what they had done before. I did not date for people.
Yeah.
And yeah, it was what I got out of it. There's always the 3 different levels, the file tracking, the meta level, and the variable level tracking. So they try to do it in different levels.
Mm-hmm.
And I guess that's what to try to make it kind of, I don't know, complex to avoid hiding information away from them in some way. That's why I try to see it. It seems like some smart guys really understanding the architecture behind it and know how to build this one to really capture everything going out of your phone.
That's right.
So
Yeah.
that's my understanding of it.
Yeah, so they were really doing it on the kind of operating system level and capturing exactly the function calls and the variables which are passed around. So if I read something, then they were tracking who has access to that, where it was passed. You can do it sort of higher level tracking of having a proxy and just capturing everything which goes out of your phone, right?
Which was written in this one that someone had did before.
Yes.
Yeah. What I didn't understand was how they really could capture the right things in some way, even down in the details. When I saw some of those, when you went into the stacks,
Yeah.
and how did they really capture the right stuff, that was difficult for me to understand.
Yeah, so the key diagram is the one on page, the figure 2, right?
Yeah.
So that kind of captures the whole concept behind the paper. So you have a taint source. A taint source is what's being tainted. So you can say, for example, we're gonna track the location. Who is using location? And every time the locations manager is asked for the location, it gives the location together with the taint, right? So every time the location goes out, it goes out together with the taint. And then it kind of goes all the way to the untrusted application, and untrusted application does something with it. And the untrusted application will pass it either to the network stack or to library or whatever, which kind of can read the taint. So you have the trusted library, usually low-level library, which sort of, for example, passes it to a network stack, right? So if the untrusted application got the location and then passed it somewhere else, we can detect it by the taint sync. So then you can track who got it, who requested it, and how they used it, right? On a very fine granularity level, on a kind of variable level, because we're tainting the variables exactly where it is stored on the kind of execution stack. Yeah, so that's kind of how how it kind of works in a high-level explanation. And yeah, they had some results, and they've done the study twice. They've done the study in 2010 and then repeated in 2012. And what were the results?
I guess it was increased. It was written at the beginning. Yeah, okay, similar approach. So it's the same.
Yeah, so the results were the similar, and majority of the apps were kind of using the information for various purposes, for advertising or for passing it to the backend server. Yeah, so since 2012, some of the things have changed. And for example, if you're publishing an app, you have to have a clear privacy policy. So all apps on Google Play should have a URL or some accessible privacy policy which the users can check. If they don't, they can be pulled out of the market. You can report it, and then Google will pull them out. So Apple makes an active kind of verification process. So they kind of check your apps before they are published, whereas Google does the reverse. It publishes kind of everything, and then you can report if things are not as they should be, and then they will pull the app off the market if they decide there is a violation of the terms of service. And one of the rules of publishing is that you have to have a privacy policy. So you have to clearly define of what you ask user to provide and what you do with the data, and how you store it, for what purpose, and what you give out. Also, if you're using Google Analytics, any of you use Google Analytics? They also tell you that you have to tell the user that you're using it, and you have to have the user should have the ability to opt out, right? So if you're using Google Analytics for a mobile app, you should have it in your privacy policy, and you should give the user the ability to opt out, to turn off the analytics if they don't want to be tracked, in theory. Yeah, turning things off is not hard. Kind of one article, really, but it's sort of difficult to integrate everything kind of in a good user experience. Yeah. So sometimes you kind of some apps don't do that. Right. So what else changed? So some of the things changed were the kind of the types of permissions have changed since then. The terms of service and publishing on Google Play has changed slightly. So the privacy policy is now the kind of a fundamental thing that needs to be done. What else has changed? So what was one of the technical challenges they were discussing in the paper, which came out with 2.3, with Android 2.3?
Access to native services.
Yeah, so they couldn't really do the native stuff, so they tried to exclude it, right? So they did a site study, which they refer to, and they said that 5% of apps, of all the apps, use what? Native extensions, right? So they use something with the .so, with the package. Yeah.
Okay.
Yeah, so that was one of the kind of relevant pieces of information. The other one with 2.3, yeah, I think it was 3.
So that's not a problem anymore? Is that what you're saying? It's not allowed to use this .so?
No, it is allowed. Yeah, it is allowed, and more apps probably now use that than before. Most OpenCV, for example, apps will use the OpenCV extension, the native extension. So native extensions kind of got easier now.
Okay.
But with 2.3, they talked about just-in-time compilation, right? Just-in-time compiler. So how does that work? So some of the things they were using kind of required the instrumentation. It required the bytecode kind of manipulation and virtual machine integration. And then JIT kind of messes things up because it does things on the fly. It sort of compiles things when needed and kind of changes some of the placement in memory of how things are kind of laid out. But once it's done, it's done. So it kind of is cached, and then you can use it. So
it's not there anymore, or is it just?
yeah. So now we have something which is called what? What's that for? What that stands for? Right. So that one is
Just in time.
yeah, just in time.
Almost too late.
And the other one?
Ahead of time.
What?
Ahead of time.
Ahead of time. Excellent. So that one is kind of a more modern technology which allows you to pre-compile everything before the app actually needs it. So just in time was sort of warming up, and as some things were kind of being used, they were compiled when they were being used. So part of the application might wait until very, very late to get compiled because it hasn't been used initially. With ahead of time, you start to bootstrap your application, and in the background, the ahead of time compiler kind of works out what to compile and kind of starts compiling everything. And it builds up the native version of the app, and then you kind of run the native one. So it starts by running some of the interpreted code, but as it starts, it kind of pre-compiles everything, and then you have everything kind of ready, even when you don't need it. So it's sort of, it has one advantage and one disadvantage. The disadvantage is that, yeah, you use more memory and you have initial lag between things that actually work because you have to kind of pre-compile it. But then you don't have the, during the runtime, you don't have the lag. Whereas with just-in-time compiler, you start immediately but slow, and then you get faster and faster as you go. But you have this kind of laggy compilation stages once you hit the parts which were not compiled yet. And you need them, right? Because it doesn't compile ahead of time. It compiles when you need it. So you need this functionality. It's not there. It's being compiled, so there is a delay, right? With this one, you need that functionality. You already have it immediately because it was pre-compiled before you needed it. So there are some trade-offs, but with the modern multi-core systems, you can do a lot of stuff in the background, so you usually don't notice that the phone was actually compiling something in the background when you were, opening the opening screen or something. So things kind of happen pretty streamlined. You do have a more, slightly more memory consumption, but again, it's temporary because once it's compiled, it kind of clears the memory from the not native extended code which you initially loaded. So you only need to leave the native compiled code. Right. So this kind of architecture should still work with the modern thing, although they kind of migrated a little bit from the Dalvik to the new virtual machine, which is slightly different. So the modern 5.0 and onwards phones, they don't run Dalvik by default anymore, right? So if you check what sort of virtual, so who is running 5? And you?
I don't know. I don't know.
Yeah.
Double check. Settings? Or
Wasn't the Android runtime introduced in 4.4?
4.4, yes, that's right.
Yeah, Field Runners 2 stopped running. And then you changed to.
okay.
What's that?
The Field Runners 2 game stopped working if you switch to ART.
Yeah, exactly. So there is a new.
No point of having ART.
I don't think they have the option to switch to Dalvik anymore.
Maybe they removed it in 5 now.
I don't see it in 5. It was still in 4.4.
Yeah,
You
but the difference was that in 4.4 this was optional, but whereas in 5.0 it was mandatory.
Yeah, exactly.
They only introduced it in 4.4 for developers to try it out and get used to the system.
Exactly. That's exactly the case. So I don't think you can change it anymore. You kind of forced to use ART from 5 onwards. So there is a slightly different virtual machine which allows even easier instrumentation than Dalvik, and you can kind of do more on the fly and more kind of debugging and instrumentation facilities, because the phone got kind of more complicated and they need a more robust API to do that. So it is quite well designed, and it's quite fascinating how things kind of improved over the years. But it has a bearing on the article, because some of the things which were easily doable with the Dalvik app may not be as kind of not the same with ART. So there are some things I want you to remember from this paper. So I want you to know what the difference is between Dalvik and ART. That ART is the new kind of virtual machine, and Dalvik was the previous one. You should know some of the advantages of using ART. I would like you to know the permission systems, how it works with Android, and what differences it has to iOS. How people do tracking. So there are proxy apps which you can install, and they kind of notify you when anything leaves your phone over the network. So you can sort of see what comes in and what leaves your phone. It's not on the level of detail of this paper, but it still gives you some indication of what you might be leaking, what information your phone leaks to the external services, and to whom the phone makes connection, like to whom the data is being passed. I don't require you to understand fully how this works. It is quite detailed, and you need to sort of understand computer architectures quite well to sort of follow that one. One interesting aspect which you should know as well is the difference between register and stack-based virtual machines. Yeah, you know what virtual machine is? What is a virtual machine?
A virtual?
Yeah.
Virtual machine.
Yeah.
So, yeah, anyone? We said it a lot of times actually. It runs like just in time, or pre-compile the code, so it's byte code pre-compile, and you can then make the codes. So that's the difference. So you have to compile the code before running.
So why is it called virtual machine?
Because it's running on top of the other one.
Yeah. Good
And
point.
I just saw an Android, you spin off another one for every time you have an application. So each application has each virtual machine.
So we have the hardware. So we have the hardware. What sits on top of the hardware? What touches the hardware?
Native system.
Drivers.
Drivers. What uses the drivers? Operating system. So that's the native stuff, right? So there is kind of a bit of a layer between the OS and the hardware. Those are the drivers. And then you sort of have all the facilities, all the memory management, and so on. You don't do it on the memory. You do it via the native OS services. So you don't need drivers for everything. Some things the operating system kind of controls directly. So you have, it talks directly to the memory controller, but it doesn't talk directly to the sound card or microphone. It does it through that layer, right? So you have kind of like that. And then, so the hardware kind of is an abstraction. So say yeah, say here. Here we have kind of an abstraction. So if I talk to the operating system from here, it's as if me talking to this kind of abstraction, which tells me there is something which is kind of for storing, like memory. I have something for doing kind of computing. So I have something like a CPU. I have some sort of I/O, and I have kind of those concepts, right? So conceptually, I have this, and this kind of CPU plus memory plus I/O is like a machine, it's like a computer, right? So if I talk to the operating system, it's sort of like me talking to a computer, right? So this is kind of the conceptual representation of what is here. And then I have a VM. So I have a virtual machine which talks to the operating system and does facilities for me, but my application kind of talks to the VM, right? But when my application talks to the VM, the perspective the app has, it's kind of the same as this one. There is still kind of the idea of having a CPU and the idea of having a memory and having kind of some sort of I/O and so on, right? So the app running on top of the VM sees a certain perspective of how this computer works. And then the VM running on the native sees certain perspective of how this works. And then the actual hardware is the physical machine which runs stuff, right? So this machine, and this machine all share some concepts. They share a concept of memory management, they share a concept of the CPU, how the CPU works, and they share some concept about I/O. But they don't have to be the same. And in fact, they typically are not, right? So let's say, if you run Java, so if I run Java VM on top of the Windows OS, which runs on top of my Intel x86 CPU, right? The Java VM computer, which it runs on, is using stack. Windows and x86 both use register. Register-based computing, right? So you can have a CPU which is stack-based or register-based. What's the difference? Well, the difference is if I have internally a CPU, if I expand that, I have an ALU. So I have some sort of arithmetic logic unit, right? And with the register CPU, like Intel or AMD or what have not, you have kind of an area inside the die of the CPU where I have the registers, and my instruction set tells me to do operations on the registers. So for example, if I have a memory, I have a memory controller, and I have my memory there. One of the instructions can be read particular location of the memory into that particular register, like AX, right? So this memory value gets written here. Another instruction may say, okay, read the other one to BX. So I read that one to here. And then I can say, add those two values, add those two registers, and store the result in this register, right? So I can have an instruction which says AX plus BX and store it into AX, right? And then another one can be write value of AX somewhere in the memory, right? So I have, it's sort of like a cache, some kind of a very fast local kind of space where I store data and kind of I pass it back and forth inside the memory. But I have those registers and they have names, and my instruction set uses them to do stuff, right? So the instruction set looks like the instruction has what to do from to, right? So usually it has three parts. What needs to be done, from where to where, and usually that or that, one of them is a register, or both of them are registers, right? You don't have instructions which do stuff on memory directly. You always have stuff to fetch from memory here, do stuff here, and push somewhere there, right? So this one is either register, or that one is a register, or both are registers, but you cannot have two memory things together. You have one register and one memory on one of the sides, or on two registers, right? So that's the kind of the instruction set. With the stack-based CPU, it looks differently. So stack-based CPU looks like that. Again, you have the memory controller, you have your memory there, you have your ALU, and you have a stack. What's a stack?
Just put it on the top of it.
Exactly. It's kind of like a tabletop, which you can put stuff on top, right? So now, if I have, okay, so you have this image in your head. I wipe it. Right? So now I just have a tabletop here. What instructions can I have? Well, I can fetch stuff from memory onto the stack, right? So I can have what to do. So I can say fetch from. I don't need to say where, because it always ends up on top of the stack, right? So I can say copy this to here. So I have this value here. Copy that value on top of the stack, right? And now I can say add. I don't need to say from where to where, because I always add the two top items on the stack, right? So my instruction set is much simpler, right? I don't have three parts anymore. I have one or two parts, and if I have the second part, it's always about the memory, right? So I either have what to do, and what needs to be done is always taking arguments from the stack, or I have transfers, and I'm always transferring from memory or to memory, right? So I can say push the top value from the stack to the address, which is the second argument on the stack, and so on, right? So I am kind of, those are memory locations. I fetch those from the stack as well, right? So in fact, I kind of don't have these neither, because I always, if I need to fetch something from memory, so if I have an empty stack and I want to put on top of the stack the value of that memory address, I have to generate that address onto the stack first. And it's sort of like pushing a constant, right? So I kind of, I have something here, which is a constant, which I push on the stack, and then I say fetch from this address on top of the stack. So that is deleted, and then the value of that cell ends up here. Does it make sense? So the point here is that the instruction set of the stack-based machine is very simple, because it doesn't care about the operands. The operands are always taken from the stack and pushed onto the stack. With the register-based machine, it's more complicated, because you have to say which registers is being used currently, and it sort of makes the codes more compact, right? So if I need to add two numbers with the register-based machine, how many instructions I would have to use? You would have to use kind of move. So you're moving from memory to register. If I'm adding two numbers, so it will be another move from the second number. Now, two registers, I have two values. Then I will have add. So I'm adding those two registers, and I have the result in, let's say, AX. And then I would have the move back from moving that data back. So I use 4 instructions, right? With the stack, how many instructions I have to use? Well, first I have to say, I have to put that address of where to get stuff from. Then I will have to do the fetch, right? So address, fetch. Repeat that twice. Put and fetch. So now I twice put some address here and got the value. Put another address, got the value. So now I have two values. Then I would do add. Then I have to put a new address of where the result should go in. And then I will say, yeah, move or whatever the instruction is, right? So I have 1, 2, 3, 4, 5, 6, 7, right? So the same logic here is only 4 instructions, but they have multiple parts. Here it's 7 instructions, but they are very simple instructions, right? My instruction set is very small. The instruction set here is quite complex because for move, I have, move from memory to AX, move from memory to BX, move from memory to CX, blah, blah, blah. I have multiple things. I have multiples of moving. Here I have just one way of doing it. It's putting the address and fetching it. That's it. There's only one instruction for fetching stuff from memory to the stack. So a short summary of that is that for this, they said, well, we have a lot of complications here, but we can optimize for register-based CPU ourselves, and we want the Java virtual machine to be implemented for multiple platforms and be as simple as possible. So they implemented that as a stack machine, right? So the stack machine has this instruction set. So the Java bytecode is using a stack logic to do all the operations, all the copying to memory and from memory and doing some logical operations. Whereas the Windows kind of operates on registers because it's very tightly coupled with the hardware, with the actual hardware on which it runs. And the hardware is register-based. There are no commercial stack-based CPUs anymore. There were some when the Lisp machines were being produced, but it is much simpler and much faster to implement stuff using register-based machines. So now most commercial CPUs are using registers. They don't use stack. But the virtual machine is using a stack, right? So when Dalvik came about, when they were implementing a virtual machine for the mobile system, they said, well, this is great. I mean, the stack-based VM is great, but it's so hard to be optimizing it for register-based hardware, right? Because you have a stack metaphor running on a register CPU. You have to have a considerable amount of logic of compiling that stuff into that stuff. And it happens kind of just in time on the device, on the mobile phone, with limited memory, limited CPU, and limited battery life, right? So they say, well, you know what? It sort of doesn't work that great for us. So when the developer who was developing Dalvik was thinking about it, they decided that for mobile stack, they will do the VM, but they will do a register-based VM, right? So now there's kind of an interesting paradox. You're writing, for Android, you're writing in Java.
For new Android, you have the register-based, what are you saying?
That's right. So what I'm saying is that on Android, you're writing stuff in Java, which gets compiled into .class. And .class is stack-based, right? It has a stack-based bytecode. Then you compile it again into Dalvik, which is another VM which runs register-based VM, right? So even though your app is written in Java, and it uses one VM, which is stack-based Java virtual machine, it actually is compiled again into another VM, which is Dalvik, which is register-based. And that one is compiled again into a native code, right? So you have 3 stages.
Yeah.
With this stage being done on a PC.
Yeah,
So
that's the still design time compiling.
Sorry? Yeah, that's design time compiling, exactly. So they took this complexity of turning stack-based stuff into the register-based stuff and split it into 2 stages. They split it into the stage which is done on a PC when you're actually compiling your APK, once the APK is compiled, you have the register-based VM, which is much simpler to compile into the register-based hardware, into a native code. So the just-in-time compiler, or the compiler from Dalvik to native, now is simpler, because most of the complexity has been done here on a PC.
Performance thing.
Yeah. So the VM is kind of it's sort of a two-stages process with the interesting claim, because in fact Android doesn't really uses Java, right? They don't use Java VM internally. They only use the Java language for the source. They use Java language with the Java bytecode for the source, which then gets compiled into Dalvik. And Android uses Dalvik, doesn't ART now, instead of using the JVM. So there was this interesting law case suit with Oracle claiming that Android should, or Google should pay Oracle licensing fees for using Java for the Android platform. But actually, they sort of internally don't do that, right? But that kind of is against the Java terms of service, the terms of use. So the kind of, you can look it up. It has been quite interesting back and forth between Oracle and Google in terms of how they do that and how they use the language. Yeah, but anyway, so the story is that the virtual machine is sort of the perspective on the running hardware, and you can have multiple, you can chain them, and you can have machines kind of interpreting stuff for other machines and giving it until the native code. And the funny thing is that in modern implementations, in modern architectures, you actually don't have that neither, right? Because what we like is to have another layer of interaction, and we kind of have hardware here. And here we have another virtualization layer. Right? So we have another API which the drivers use, and the drivers don't actually talk to directly to the hardware, but to a layer which kind of separates us from the hardware. Right? So the virtualization layer, or Zen, Zen, or VMware, allow us to separate how the drivers see the hardware, how the drivers see the virtual machine, and what the actual hardware looks like. So we kind of making more and more interactions between what kind of runs on what and what the actual hardware looks like.
What's the reason to do that?
Yeah, so what's the reason to use Zen, for example?
I would say the negative, that must be performance again.
Yeah?
Right, normally you do this so you don't have to make drivers for each hardware anymore, just make it for the virtual machine, and the virtual machine makes the connection to the hardware. Is that the thing?
Yeah, partially. So the biggest advantage is, let's say I have a server, right? So I have a box, and let's say I have 8 cores, right? If I put a single operating system on it, it kind of occupies the whole system, right? If I have the virtualization layer, I can put a Windows and another Windows and a Linux running on the same hardware all the time concurrently.
Load balancing.
Yeah, and let's say this guy uses 3 cores, this guy uses 3 cores, and that guy uses 2 cores, right? And the same with memory, the same with I/O and network cards and so on. I can say if I have, if I have 3 different network cards, I can say, okay, you will use this one, you will use this one, and you will use this one, and then they're completely independent, right? They completely, independent. If I have one, let's say I have just one network card, and all three systems need to use network, right? If I have no virtualization layer, the driver who is plugged into this card takes the whole card, right? But now we have virtualization layer, and then I have a virtual network card to all three devices, and the virtualization layer made multiplexing for each of them to reuse the same card, pretending that, okay, you have your own one, you have your own one, and you have your own one. Same with memory. I may have, 128 gig of RAM, and I sort of say, well, there is so much RAM that all of you can use it. So on a single platform, I can host multiple services or multiple things. What we were doing with, we had a project with Sun Microsystems, and they had a machine which was a single blade server, and it had 32 cores, and later they had a 64 cores version, and you could put 2 CPUs on the motherboard, right? So you could actually have up to 128 cores on a single box, right? So it's a lot of cores for a single operating system, right? So what you can do is you can split it. You can say, okay, I will have, for example, 32 cores dedicated to one task, which was network routing. And then the remaining would be split into 3, firewall and the actual OS running the Apache and so on, and some data store, right? So you can partition it and have dedicated functionality on isolated on the same hardware, and it would kind of work because of the virtualization. So the actual hardware was here, and this layer was called hypervisor. They use the same language for Zen and for VMware. They also talk about the hypervisor being kind of the manager of the hardware, and it isolates. So nobody talks to the hardware directly. They all talk, the operating systems and all those components talk to the hypervisor first, and it kind of makes the calls. It kind of, yeah, you're right. It sort of slows things down in a sense, right? Because it adds this extra layer of indirection. But with Intel, I don't know, you go to your BIOS, you have a PC. So go to BIOS, and you can see that you have the ability to turn on virtualization on the CPU level, right? So actually, this hypervisor layer is kind of part of the hardware now. It's kind of part of the die. The die allows you to do that, right? And there is almost no performance penalty. It can kind of split the cores into multiple channels, and you almost pay no performance penalty for running multiple things on the same hardware.
But if you go back to application development, there's nothing you can do on that layer, of course, that impact that.
No, yeah.
It's done way
below, yeah, exactly.
Yeah, by this virtual machine layer, of course.
Yeah, that's right. Yes?
Is it possible to use this virtualization in our edge?
Yeah, it is. It is possible, and a lot of teams do that. For example, a lot of teams work using virtualization to package like the IDE and everything into a kind of a VM, and then you just open that VM, you do your development, you shut it, and the same VM is run by all the developers. So they always have the same version of IDE and the same version of the software and so on. So things kind of got quite interesting in terms of this virtualization stack. I was just reading the other day kind of component architecture where you're developing a web app, but instead of launching it on Apache or whatever, you want to launch it on a kind of a component provider which separates you from the actual hardware, right? So you have a layer of indirection on what you're running it, and then you can deploy your app on laptop or on a server or whatever, and you don't care because it's sort of separated from the hardware by this kind of manager layer. So there is a push to kind of make it more compartmentalized and more managed, that you kind of have control of some of the facilities and some of the provisioning. For the normal mobile apps, there is little point doing that though, right? So the mobile apps are isolated, as you were saying, by having a VM per app. So each app runs in its own isolated VM. So if it crashes, it only crashes that VM. So if you, for example, run an app which keeps allocating memory, right, and crashing the VM, only your app will crash, nothing else will be affected, because although, yeah, probably you will not affect anybody else, even if you kind of exceed the memory. The other apps will get the notification that the system is running low in memory, but they will not get killed. Only your VM is gonna get killed. So you have kind of isolation already as part of the operating system, and Android does it quite well. You have an overhead though, because normally if you have two apps running in the same process space, sharing data is very simple because they kind of can share, resources. If they both run on the different VMs, sharing data is not that simple because they have to either write to a file or use a network or somehow communicate with each other, right? So you have, on Android, you have this sort of a notion of intents, and they kind of actually go through the network stack. You're passing the notifications kind of as if they were separate processes. When you're running your own app, you can decide whether you only use one VM or multiple VMs too. So your activities, you can spawn them. By default, they are spawned in the same process, but you can mark them that if somebody needs that new activity, you actually start a new VM. And even within a single app, you can have multiple VMs to isolate things better. So yeah, kind of understanding how that works kind of help to design your apps. All right, so we kind of ran out of time a little bit. I sidetracked a little bit to talk about the VMs. So we didn't talk about the repeatability and reproducibility of the research. So can you guys read that paper for tomorrow? And we will discuss that one. If you have other interesting articles about doing research or doing research well, email me and I will put them onto the list as well. But that one is reasonably easy to read and short, so please read that one. And we will see each other tomorrow. Yeah, thanks.